Hey everyone, so I wanted to continue our discussion about horizontal projectile motions. Now, like I said before, we're continuing this from Unit 1, but it's now being moved to Unit 3, so make sure that you're in the right section. We already started talking about this in class, but just as a quick recap, remember with the horizontal projectiles, basically the idea is that unlike the other projectile what we did, where the object is thrown vertically upwards, we're going to be throwing the object vertically horizontally. So it's going to be given an initial velocity in the horizontal. However, the acceleration is still only acting in the vertical direction due to gravity, just like what we had in the other projectile that we see. And as we saw in class, we have to kind of treat this very carefully. And what we'll have to do is create a chart that takes into account what's going on vertically and horizontally because the velocity in the x direction is unaffected by the acceleration in the vertical direction. Motion horizontally is independent of motion vertically. We kind of saw that with forces and how we kind of dealt with horizontal forces separately from vertical forces. So it's just a continuation of a lot of that stuff. Now, we already should have done some problems in class. So what I'm doing is I'm going to give you two more additional practice questions that are not in the notes before we start going over some other small things that are in the notes. For the most part, this is kind of just a little bit of recap plus a little bit of small extension. All right, so here's the first question. Pause video or itself, and we'll go over it in a second. All right, so the question asks, how much time has passed before the ball lands on the ground? We had this ball being thrown horizontally from the top of a roof with some initial speed. So this is the first part. Like I said, the first thing we want to do is just record all the information to an XY chart. When we do that, our XY chart looks like this. For the most part, a lot of these terms, remember, are consistent. Like the initial position, the x is almost always 0. The final position, the y is almost always 0. Initial velocity is 0 in the y, and the accelerations 0 and -10 respectively. We are given the initial velocity in the x direction, which we also know is the final velocity in the x direction because of the 0 acceleration. And I know that the initial position, the y direction, is 75. Again, imagine putting, just like in the previous problems that we've done with projectiles, imagine putting this problem onto a grid and you're kind of looking at it as if, the position is kind of where it is on the y and x axis. So in order to figure out how much time passes before it lands on the ground, we are not going to use the x direction. Remember, the x direction does not have nearly enough information on it. The only time I can use the x direction is if I'm only missing one piece of information. I'm missing two, I'm missing x and t, so I want to use the y direction. For the most part, that is what we kind of want to look at first. We look at the y direction. We're going to use the annoying x equation. I'm just replacing the x with y's here just to kind of keep in mind to myself that I only want to focus on the y direction. Make sure that you are not crossing the streams. You're not taking terms from one column and combining it with terms from another column. So we use this annoying x equation. We use the y values, the 75 for the final, the initial position, 0 for the final, 0 for the initial velocity, and -10 for the acceleration. Move some things around, solve for t, and we get 3.87 as my final answer. All right. Follow-up question, part B. How far from the base of the cliff will the ball land? So what I can do is I can use my exact same chart. This time I'm actually replacing time with 3.87. And now what we can see is I'm looking for this x term. That's the only thing missing in this column. So I can now use the x side. I once again use the annoying x equation. This time I'm using x properly. Plug in my given information and I get that the final position is 56.5 meters. Now, the third part is a little bit tricky. So it wants to know the ball's total velocity. So one thing we could think of is that, well, there's going to be a final velocity in both the x and the y direction. Now, currently, I'm missing the y direction. So why don't we figure out what that is? So I'm going to use the acceleration equation, v naught plus at, with my given information. 10 times 3.87 gets me 38.7 meters per second. Now I have the final velocity. The question is, how do I find the total velocity? Because I have a velocity in the x and a velocity in the y. Well, this is where we kind of use our Pythagorean theorem. We have a velocity in the x, so we have an x side, we have a y side. So I can use Pythagorean theorem, a squared plus b squared equals c squared, to determine the total velocity. I will say that this is not a super common question. It is just something that you want to keep in mind, though. So we plug in the x component, we plug in the y component, we square them and then add them, and then I get 41.4 meters per second. Be very careful. Just keep in mind, I put in a negative here and the negative into here, but if you put this into the calculator incorrectly, there's a chance that even though when you square a negative number, it should be positive, you might accidentally make it where technically the negative is not being squared. So just be super careful, put parentheses, or you could just drop the negative because you know that the square of a negative number is always positive. So why even bother including it in? All right. There's going to be one more question. So here it is. Pause the video, work itself, and we'll go in a second. All right, this one's a little bit tricky. I don't really have the space to put the diagram on, but we have a block on a table. It's going to be shot off by a spring. It flies off the table and lands on the ground. Here, what they're doing is they're going to give us the initial height of the table. We know the landing spot of the on the floor, and they want to know what the time is in the air and the initial speed of the block as it leaves the table. So this is what my chart looks like. So just like last time, to find the time, I use the annoying x equation using the y values, because again, I have too much information missing in this x side. So I plug in my numbers given to me, and I get that the time is 0.4 seconds. Now, to find the speed of the block as it leaves the table, once again, I put that new time in, and now I do have enough information to use the x. Now, really quick, you might notice that I technically have two missing spots in this column, but remember that once I have one, I know the other. So for the most part, this is considered as one piece of information. So just like last time, annoying x, plug the numbers in, and end up getting 3 meters per second. That should be in meters per second over here. So for the most part, the horizontal projectiles really are not that crazy. What it really comes down to is making sure that you make this chart and you plug the numbers in where they belong. And again, don't cross the streams. The biggest struggle that people have is reading the question and determining where something goes inside the chart. Depending on what level question you're dealing with, a lot of the regions questions will tend to keep this to single problem, while some AP questions might throw a few curveballs here and there, but nothing too crazy. All right. So one thing that you're going to need to know is how certain factors affect a horizontal projectile. This is going to be extremely important for a lot of multiple choice questions for both the regions and AP level. And you're going to want to know this regardless of what type of values are going on. So like for example, mass. Does mass affect things like range and time in the air? Just to clarify, range is referring to how far away from the like horizontal distance, how far from the table or cliff or wherever the object lands, and time in the air is how long it's in the air before it lands on the ground. Well, does mass affect it? No. We haven't really included mass in any of the problems, so mass has no effect. What about height? Does height affect range and time in the air? Well, what height does is it keeps it in the air longer. So the higher the object is, the longer it's going to be in the time, time in the air. And if it's going to be in the air longer, that means it should be going much further. What I recommend is go extreme. Imagine rolling something off of your table and then imagine rolling it off the top of a building. You can clearly tell that one's going to be in the air longer, the one from the top of the building. And again, you could probably make a estimate of whether or not that's going to go further or not. The next one, what about horizontal velocity? Does that affect range or time in the air? Well, we definitely know that it's going to affect the range. I mean, it's a horizontal velocity. So increase the velocity, you increase that range. We saw it in a bunch of problems. But what about time in the air? No. The time in the air is dependent only on the y values. So making it go faster does not mean it's going to land faster. It's just going to land the same time as always. Technically, in the real world, that's not necessarily true. Increasing the horizontal velocity actually does make it stay in the air longer. if it is at a fast enough speed where the curvature of Earth actually ends up being an issue. But I don't see that being an actual problem or thing that you're going to have to consider. And then you could think about two other factors that could affect the range or time in the air, and how that affects it. So gravity's one. Gravity's a major thing. You should know how gravity affects range or time in the air. So for gravity, if you increase the gravitational acceleration, objects gonna fall at a much faster rate. So we know that the time in the air is going to change because that is a y value. And in that case, if the acceleration increases, then we know that the time in the air should end up decreasing because it's going to land faster. And if that time decreases, we know that the range should also decrease. Another factor you can think of is air friction. How would air friction affect this stuff? This one is going to be a little bit trickier because it's going to increase the time in the air, but it's also going to decrease the horizontal range. This one's, like I said, a little bit harder to think about, but it does kind of make sense again if you go extreme. If you have really bad air friction acting on the object, then it's going to take longer because the acceleration is essentially smaller. So it's going to take longer in the air. But even though technically increasing the time in the air should increase the range, because again they have a direct relationship. Because now the horizontal velocity is going to be experiencing a deceleration in the x direction, unlike our ideal problems. It means that that increase in time is actually not going to be enough to deal with that decrease in horizontal velocity, that decreased acceleration. So it's actually going to slow down and not go nearly as far. All right. So these are some main things that you want to be able to keep in mind. This was something that we already saw in that first problem. Like I said, it's not super important, but just be aware about the difference between the velocity in the x direction, the velocity in the y direction, compared to the final velocity. So if the final velocity, they're asking about that, that basically means they want you to combine the x and y directions, just like we saw in the problem, and they want the Pythagorean theorem version, essentially the resultant of those two components. All right, now there are two more problems. These problems are actually in notes, but they're not calculation-based questions. So here's the first one. Pause video, work itself. We'll go over a second. All right. So the question is, sketch the graph for the projectile if it was non-ideal. So this dotted line is supposed to represent the ideal path. The whole idea about ideal versus non-ideal is basically a way of them saying no air friction and air friction. So this path is the path it would take without air friction. So they want us to figure out what the path would look like if it did have air friction. Well, as I said before, if we introduced air friction to a projectile, it's not going to go nearly as far. That's pretty much the main thing. That air friction causes the object to not go as far, as fast, for as long. So this projectile is going to land somewhere over here. I don't know. But everything else should be the same. You're still going to make it have this parabolic path. It's just going to end up lower. So you don't want to go any crazy with that path. So it just looks like this. Again, should follow the path in the beginning because for the most part, air friction is one of those things that doesn't make an immediate appearance right off the bat. It takes a while as it speeds up before we start noticing more and more. So it follows the path initially and then starts deviating and just lands a little bit earlier. That's it. All right, here's the next question. Pause the video itself and we'll go over in a second. All right, so this one's going to be surprisingly tricky. So we have a person swinging on rope and they're going to release, there's 3 different points that it could release at, and they want us to sketch the path that it takes. So we have B, C, and D. Now, if it releases at B, this is actually a very, I shouldn't say unique, but this is just another horizontal projectile. By the time it reaches B, it's going to have a horizontal velocity because the velocity is always going to go tangent to the path it's traveling. So when it releases, this is just Newton's first law that the object will keep moving in a straight line. So when it releases at this point, the velocity should continue being in a straight line. So it just looks like a horizontal projectile. Now at C, C, it kind of releases up at an angle, again, in a straight line from this point, tangent to its path. We haven't done angular projectiles yet, but for the most part, it's going to follow something that looks like that. And again, it's still a parabola. That's the big thing about all these projectiles is they're technically parabolas. We're just looking at them at different segments. Here, we're looking at the parabola from the peak to the ground. Here, we're going to look at it a little bit before it reaches the peak and then it goes to the ground. Now, what about D? Now, you might think that D follows the same thing. When it gets to D, it should have a velocity that goes up, and it should follow another, maybe a very steeper version of this parabola. Except one thing that we're going to learn, it says that it reaches a maximum height at point D. Now, if we think back to the first time we talked about projectiles, what do we know about the term max height? We know that the velocity, at least in the y direction, is 0 at max height. So at point D, it has no velocity, which means when it releases, it's going to go straight down. And that's it. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.